In the world of functions, we have some important properties for functions. A function is defined injective, surjective, or bijective. So a function can be injective or one-to-one, or it is surjective onto, or bijective, which is one-to-one and onto. So let us define each one of these separately and go over examples. Let f maps x to y. We say that f is one-to-one or injective if it passes horizontal line test. If f of x1 is equal to f of x2, then you can conclude that x1 is equal to x2. Or if x1 is different from x2, then you can conclude that the y values are different from each other. Remember that in pre-calculus, in algebra, we call this the horizontal line test. It was important in finding the inverse of functions. When you have injective or one-to-one function, you can define the inverse of the function. Very good. Now let us define onto functions and then go over examples. Let f maps x to y. We say that f is onto or surjective if for any y value, you can definitely find an x value. So if you take any y value in y, for sure you have an x value that connects x to y. So if and only if for any y in y, we can find x in x such that y is equal to f of x. So the definition of onto surjective, the definition of one-to-one injective, and we say that the function is bijective if it's one-to-one and onto at the same time. Okay, so give us an example. Take a look at the following example here. Analyzing a function being one-to-one or injective is easy. Sometimes students have difficulty with being surjective. Example. Is the function, I'm going to define the function like this, f which is defined as a linear function mapping R to R, f of x is equal to, for x minus 1, for all x in R. Injective, surjective, one-to-one, onto. Okay. This guy is just a linear function, all right? F of x equals to 4x minus 1 for all x in R is a linear function. So for any sets of points, it passes the horizontal line test. So let me write this down. It passes the horizontal line test. So it is 1-to-1. Or you can take the definition and write it this way. You can say that, hey, if x1 is different from x2, then if I multiply both sides by 4, 4x1 is different from 4x2. If I subtract 1 from both sides, 4x1 minus 1 is different for x2 minus 1. So it means that f of x1 is different from f of x2. Y values are different. So it is a 1-to-1 function. Now for being onto. So here we just showed that this is 1-to-1. To show that this function is surjective or onto, we take y belongs to y, which is R. Okay, very good. Can we find x in x such that f of x is equal to y? Well, let's check the definition of this function. This is y equals to 4x minus 1. Since y value is defined as 4x minus 1, it means that y plus 1 is equal to 4x, am I right? Or y plus 1 divided by 4 equals to x. So for any y, we can define x to be y plus 1 over 4. Just do a simple algebra. Add 1 to y and divide it by 4. Is this a real number? Of course, which belongs to R. So we just showed that f is onto. It wasn't that hard, it wasn't that difficult. I did the algebra, this fraction is a real number, so I'm done. I just showed that for any y, I can define x. So x and y are connected together by this function. So if I just plug in x into this function, I get my y back. So that's how we show that it is 1-to-1 and it is onto. In another word, you have a bijective function here. Now let us go over another example. I'm going to change the domain and the codomain of the function. Take a look at this. I'm going to make some adjustments here. Now I'm going to define f to be a function that maps z to z, integers to integers, and f of n is 4n minus 1 for all n in z integers. Is it onto? Is it one-to-one? What's the deal with this guy? So for one-to-one, let's follow the definition. You can use this one or this one, it doesn't matter. If f of x1 is equal to f of x2, you need to show that x1 and x2 are equal to each other. So here you have f of n1 equals to f of n2. Y values are the same. It means that 4n1 minus 1 is equal to 4n2 minus 1. So add 1 to both sides. You get 4n1 equals to 4n2. Divide by 4, and n1 is equal to n2. So it passes the definition of one-to-one function. This is a one-to-one function. One-to-one or injective function. So far, so good. Now let us check to see if it's onto surjective or not. Onto. Well, we need to show that for any y value in Z, you can find x value or n value in Z such that f of n is equal to y. This is our goal. This is what we try to find. Okay, so you might say that, hey, by doing the algebra, I'm going to come up with the exact same thing that we did before. Well, so for any integer, since I have y equals to 4n minus 1, I'm going to do a little bit of algebra here. 4n is equal to y plus 1. Then I'm going to divide by 4, and n is y plus 1 over 4. But is this going to be always in Z? For any integer, can I find another integer like n? Is it possible to do that? Remember that not all fractions represents integers. Take a look at this. If we take any integer, it must work for any integer, all right? If we take y to be equal to 0, n becomes 1/4, which is not an integer. So you are not able to find an integer connecting to 0 by this function f. That's impossible. So there are y values in Z that cannot be related to n by f. So it is not onto. Not onto.